Okay, so good afternoon, everybody out there, and it is my pleasure to kick off the latest of the Machine Learning for Science seminar. So today, our special guest is Kieron Burke, who is not just one of the leading experts in density functional theory, he's also a friend. And also, I think this is a particularly welcome talk because it's 7 a.m. In his time zone. So this is like a morning running before everybody wake up. I think for those of you who don't know, Kieron is actually is a fellow Trinity College student some time ago. And then he went off essentially to the US to work with Walter Cohn and with John Perdue and all the famous people in DFT, and he became a famous person himself. For those of you who might not know it, is the B of the famous PBE functional, and he also made a lot of other contribution in time dependent and all aspects of density functional theory. So I guess without any further ado, I'll give the stage to you, Kieron.
Thank you very much, Stefano, and it's a great pleasure to be here in Ireland giving this talk. Oh, wait, no, I'm not. I'm still in California. Let me see if I can share my screen. Yeah. Start sharing. And where's my PowerPoint? There. Okay. So, Stefano, can you see my PowerPoint?
Yeah, that's good.
Okay. So thank you very much for tuning in. And I'm going to talk about looking at whether or not you can use machine learning to improve density functional theory. And I'll also, if I have time toward the end, give some general comments about machine learning in physical sciences. So I started working in this area about 10 years ago, when I was very lucky to meet another person who's become a good friend, Klaus Robert Mueller at TU Berlin, who's one of the gurus of machine learning. And we met at a mathematics conference, in fact, and we both gave pedagogical talks about our areas, and then we started betting on whether or not you could use the machine learning to find density functionals. And that's how my interest started. And that was about 10 years ago. And so I've watched the field develop. Not so many people were doing machine learning back then. And I'll sort of try to report on my observations, as well as giving you a sense of mostly what we've been doing. But the papers have lots of references to lots of other work. And yes, in fact, all the papers can be got online from this little website that I have here. That you can find them there. Okay, so first, a very, very quick review of electronic structure from my point of view, let's say. So this is the first slide I ever made when I started doing DFT about 25 or 30 years ago. And we used to hand draw these slides, and what they all have in common is it's a bunch of nuclei held together by electrons, and the electrons are all identical. And if you can, within the Born-Oppenheimer approximation, if you can find the ground state energy of the electrons in any system, then you can answer a vast number of questions, such as what is the energy to pull it apart, what are the bond lengths, bond angles, lattice parameters, and so forth. And you have to be able to do this reasonably efficiently so that you can treat a decent number of atoms in a system. And here I was testing out my iPad because I have to use it for lecturing at the moment during the virus. And you can see my handwriting isn't great. But this is the Schrödinger equation written in atomic units. And you can see that there's three terms. One is the kinetic energy of the electrons. One is the attraction to the nuclei. And the other one is the repulsion among the electrons. And it's that makes it a very painful problem to solve, because it couples the different electron coordinates together. So it's a hard quantum many-body problem. And as you increase the number of particles, the cost can scale. If you do it exactly, the cost will scale essentially exponentially. Okay. So traditional methods directly solve this equation, and that's not what we're going to do, right? And sort of our best quantum chemical method of doing this couple cluster tends to double. When you double the size, the cost increases by 128. So it really doesn't matter what size classical computer you can get your hands on. People will immediately ask you to do something twice as large as you previously did, and you'll have to wait a few years to be able to do it. So that's the problem, this barrier of cost. Okay. Now, density functional theory, in a sense, the greatest free lunch ever. So the modern version begins around in the 60s with Walter Kohn and two very famous papers. First, they prove that, in fact, you can write the whole problem as a functional of the density, and then they set up this Kohn-Sham system of equations that all the calculations these days use. And here is a picture of the helium atom. This is the exact density of the helium atom, calculated by my friend Cyrus Umbergar using quantum Monte Carlo, a very sophisticated wave function method. And here we have the external potential. And this red line here is something called Kohn-Sham potential. And the Kohn-Sham system is a fake system of non-interacting electrons, but still fermions. And you put them in this red line potential here, and it gives you the exact ground state density. And more importantly, Kohn and Sham wrote the total energy in terms of quantities you can extract from the Kohn-Sham system, plus this little piece left over called the exchange correlation. And they proved that you can get the exchange correlation potential, the potential that goes in these equations, by differentiating the exchange correlation energy. So this gives you a closed, self-consistent set of equations that you can solve for any electronic system once you have an expression for this EXC. And they wrote down the first and one of the best approximations, the local density approximation, already in their paper, and it was used for a generation in solid state physics. Today we have many more, in some sense too many more, standard approximations. So this first one is the local density approximation. The exchange you can write down on you can derive the formula by hand. Then there are these GGAs, generalized gradient approximations, and they're sort of most commonly used in materials. And then hybrids invented by Axel Becker, which mix in some exact exchange, usually in the Hartree-Fock form, with a GGA. And an example of that is B3-LIP, which is the most popular functional in chemistry today for molecular systems. So these are the standard approximations, and there are many, of course, additions to these, and people do range separation. They'll add van der Waals and things like that. But sort of behind most calculations, you'll find one of these approximations. Now, this is a picture I grabbed from a different talk that I give often, talking about climate change and how people now do DFT calculations for the parameters that go into some of these climate models. But I like this one because of the beautiful picture of the fish. And this is from an important journal in physiology, Frontiers in Physiology. And most of the paper is about sort of these farms for this fish. It's not a threatened species, but they're looking at what happens when you change the pH of the water just a tiny, tiny bit and make it a little more acidic. And what they found is that the fish's sense of smell goes way down. And what this means is they're much more liable to be eaten by predators. They use the smell to avoid the predators. And we see here in the bottom right-hand corner DFT calculations of the olfactory molecules. So I claim you can now do DFT calculations of fish and get them published in good journals. And it's important. So this enterprise has spread all over the planet. And this is from a few years ago when we did a very, very careful estimate of what's going on. And you see on the left-hand side, the axis is in kilopapers. So I estimate that last year there was probably 50,000 papers published using cone-sham DFT electronic structure. So this is now huge, and NVIDIA estimates a sixth of the world's supercomputer use is running DFT calculations. And the sad part about all this use is in none of those 50,000 calculations do they get the right answer, because they use approximate functionals and they have errors in them, right? One of the biggest problems with the whole field is that we would like our methods to be more accurate. And in fact, typically DFT calculations are not as accurate as traditional quantum chemistry. Their great value is that they are much more efficient, and so you can do systems roughly 10 times larger than you can do with a regular quantum chemistry. Okay, but one aspect of that is solving the cone-sham equations. So when we look at the many-body Schrodinger equation, this is a very difficult quantum problem, and its cost goes up very rapidly. Doing the cone-sham equations reduces that cost, but not to nothing. It goes like n cubed, the number of electrons cubed. And doing, say, 1,000 atoms on a single machine in a day is not unreasonable these days. But of course, you would like to be able to do millions. If you want to watch a crack propagate in a material, you really need maybe 10 million atoms in your simulation. Or if you want to design a drug and you want to do simulations in water, in vivo, again, you'd like to have something of the order of 10 million atoms, and you'd like to be able to run for at least a few picoseconds. And so, and even then you won't get close to equilibrating it. So there's an old problem called orbital-free DFT. The theorems of DFT say you should be able to, in fact, not have to solve the cone-sham equations if you could approximate their kinetic energy of the electrons with a pure density functional. You wouldn't have to solve them. Okay, so that's my DFT in 10 minutes, basically, right? So now I want to turn to machine learning in electronic structure, which is a very rapidly growing field. And in fact, I was very lucky to be invited to this conference a couple of years ago in Beijing, run by Tsinghua and the Institute for Advanced Study there. And we had this little meeting about machine learning in physics, and there was room for 200 people to come to the conference, and it ended up being sort of video broadcast, and 3,000 registered. And we were going to have the second one this summer, coming up in June, I think, this year, but of course it was canceled. And I want to point out we called it off very early, realizing that there were serious issues. Hopefully we'll have it next year is the plan. Okay, so a couple of years ago, I was involved with Matthias Rupp, who was a very good postdoc of Klaus Robert Mueller's when we started, and now works for a company in California, I think, but still very active in research. And Anatol von Lilienfeld, we put together a special topic in the Journal of Chemical Physics. And one of the reasons I like this is we got together, and you see there's nomenclature and there's an introduction. And half the introduction is Matthias, who's trained as a computer scientist, explaining machine learning things to the scientists. And then the other half is mostly me and Anatol going through all the papers in the issue and sort of trying to explain how the machine learning has been applied to a physical science paper. And we see again, down at the bottom right here, number of publications of machine learning in chemistry or materials. And of course, this is already, I'm sure, way out of date. And also you notice the average number of citations per article is 12, which is not bad for a topic that's only recently appeared, right? So it's a very hot topic these days. So it's taking off. So this is just a summary of some of the things that are in that special topic. It's just a slice of things. It's not comprehensive. The field moves way too fast. Okay. And here's an example that I picked at random from the recent literature, so I would call this almost a traditional use of machine learning, which I really like. Sort of almost what you find, actually, the people who really are good and understand both the good aspects of machine learning and bad aspects are often engineers, because they have actually been using it for a long time. And I had this very funny thing where I was at a meeting, and this guy gets up, and he's a really good engineer, and he's been doing this forever, and he apologizes, and he has to explain at the start that the data he's going to use is experimental. And he sort of explains what that means, because every other speaker had used data from electronic structure calculations. And, you could argue that the word data implies experimental. And so this is, a very nice use of looking at these alloys and trying to figure out their Curie temperature, and, with about 5,000 data points, and carefully, going through the machine learning algorithms and seeing what works and what doesn't. Okay. And it may have come from a place near you, right? Okay. Now, on the big scale, right, there's this Nomad lab that Claudia Draxel is very heavily involved with, this repository where they take electronic structure calculations from everywhere. I don't know when I downloaded this, but I'm sure it's out of date. There's only 50 million total energy calculations in all sorts of different codes. And the idea is you can scan through this and find, so you can do sort of searching for features to find a new good material and not have to redo the calculations. You can't really redo the calculations. It's too many, as well as, have this sort of growing database. But it's all calculations, basically, right? It's mostly DFT calculations that are going into this, and the idea is you can search for new materials capabilities. So you do sort of data analysis, that kind of stuff, in order to try to find things. A US version of this is called the Materials Project. I think originally the Materials Genome. And the slight difference, this is out of Berkeley and Gert Cedar and others. And the slight difference here is that they are generating the data themselves, and they have very sophisticated tools for people to be able to access it. So very, very sophisticated sort of workflow techniques. And, I think about 100 papers or more acknowledge this database for their research already. So these things are growing sort of around the planet. I'm sure there's about half a dozen other versions of these things. Okay. So one thing that may come to a place near you is force fields. So this is a sort of, you would think, a fairly obvious thing to do. So for, about 100 years, people have been making up force fields and learning how to run them. The original ones were things like, London dispersion forces with R to the 6 and R to the 12 potentials, and people would design these with a lot of insight and very cleverly for different problems, and you run your molecular dynamics. And these days you can, there are hundreds of force fields, let's say, for water, and Often they're not good at bond breaking. There are attempts to make them good at bond breaking. They tend to be parameterized around equilibrium of bonded sort of systems, and they're used for drug discovery and material simulations when you have very large numbers of atoms. And there's two sort of, I could think of them as distinct uses of these forces that people are now generating using machine learning. One is searching chemical compound space. So can you find taking quite a lot of elements, right? Like say a dozen, and usually the dozen that are relevant, the light ones that are relevant to medicinal chemistry, let's say. And it turns out the number of combinations you can make is vast, and you ask sort of which molecules exist that we haven't even thought of, and you want to set up these force fields to make them accurate for those kinds of searches. And then the other one is when you have a few elements, and you're doing something usually in material science where you want to do a big simulation with those few elements. You can't afford to do it with straightforward DFT calculations. So you make a force field using machine learning from data often generated by DFT. And then you can do much larger simulations. And the machine learned potentials will often be more expensive to evaluate than the old-fashioned ones, but they'll be more accurate and more transferable and so forth. So this whole field was probably set in motion, the modern version, I'd say, by Baylor and Paranello. And this is 2007, so 13 years ago, where they were comparing, this was silicon, I think, and they were comparing to the standard force fields, and they used a neural network to generate their own force field and got more accurate results than the traditional ones. Okay, and there's a nice perspective by Jorg in JCP, very, very nicely written, explaining all these kinds of things that went into that. Here's a set of physical review letters, I think. This was 2018, a good year for Gabor Sanyi, where a lot of his things came to fruition, right? And again, this is sort of more in the materials end of things, and you see that there are a lot of simulations that couldn't be done before using these gap potentials, Gaussian something processes. Okay. Oh, and look, and here's another one that I just grabbed at random. I wanted to get the published version of this, but it was published by Elsevier, and the University of California is fighting with Elsevier at the moment, and so I'm not allowed, right? But again, learning a force field now for a very specific system, zirconium boride. And again, so now this is showing that these sort of methods, you can now apply them and do simulations that you really couldn't do before. Okay. And then at the other end is the sort of medicinal kind of chemistry applications. And this is one, Klaus Robert Mueller, who I mentioned. They've been making this SGDML, which gives you very accurate forces. In fact, trained now on CCSDT, which is quantum chemical, highly accurate level to get this force field, so that you can do simulations that very, very accurately. Okay, and a US sort of alternative to that is this ANI-1. So Oscar Olex Asayev and Adrian Reutberg have developed it. And the student, Smith here, went to be a postdoc at Los Alamos, and now there are new versions of this with very sort of deep learning and very, very strong, huge computational resources behind it, making it sort of bigger and better. So the force fields, I think, are most likely the tool that will sort of start being widely used soonest coming out of this. And, I know a lot of these people, and I know these are sort of very good scientists, and it has taken 10 years of hacking away at this kind of stuff in order to produce things that might be generally useful. So that is not a small, that is not an overnight, right? Okay, so now I'm going to focus on machine learning and density functional theory, and I'll just give you some feeling for what's been going on in this area, right? And so, and of course, people have wanted to do this sort of forever. There's a paper from 25 years ago by David Tozer and Nick Handy, where they actually used a neural network to to create a new functional. And the idea is, of course, that you get data, accurate data, and you design, you make a density functional trained on the data. And I'll talk about two versions of this. One is the exchange correlation, which is the one that most people working to develop density functional theory focus on, because that's the one that you need in all those calculations. But then also we'll do a lot of stuff with this TS of n, which is the kinetic energy of the cone sham electrons. And again, if we had an accurate version of that, we could avoid solving the cone sham equations. And there's two aspects to these things. One is sort of, do you want to make something that is like what we already have, but works where the things we have at work already work, but is more accurate? And the other aspect is, do you want to create something that fixes problems that we don't know how to fix with our current functionals? Those are two different kinds of questions. Okay, so the method I mostly use is kernel ridge regression. That's what Klaus is an expert in. I call it small data. You get to 5,000 data points and stuff, and it starts becoming quite slow. And so, but what you want to do always is find these features to represent your data, and then it works very well. But you don't need, 300,000 data points like you might need to train a deep neural net. So that works very simply. This is an example. So here we have the blue points. So just think of curve fitting. The blue points are noisy data. And what you do is you write the function you want to approximate as a sum over Gaussians. You can choose other kernels with a Gaussian difference and a length scale. That's called a hyperparameter. That's a parameter you set for the whole calculation. And then you also set a noise level, another hyperparameter, which is to avoid overfitting. So if you set lambda very large, then you'll get a very smooth curve. If lambda is very small, it will thread through all the data points and it will overfit. So you apply various tricks, cross-validation tricks, where you might leave out some of your data and estimate lambda and sigma, and then do it again and again and again to find the best values and then average them. There's a whole set of routines that people do, and there are certain rules that you have to be really aware of. Like when you have a bunch of data, you take some of it and you put it aside, and that's the test data, and you can never train on the test data, which actually, if you look at the way people play games with empirical density functionals, they often violate these rules. So anyway, here we have an example, and you go through the procedure, you find the hyperparameters, and you get a reasonable fit to the original curve, which is the black line there. And unlike a lot of machine learning problems, in some sense, we can often have access to pure ground truth, meaning, there's an exact deterministic sort of value that you want to get at, but you of course only know it in limited circumstances. Okay, so and then the first one we did was this demo problem. We just put particles in a box with bumps in the bottom of the box, little Gaussian bumps with a sort of inherent dimensionality of sort of 9 parameters. We put the box on a grid, and then we just write the kinetic energy functional in terms of the density, a kernel, measuring distances between densities. So the crucial part here, and I see there's a bracket missing at the end, I think, here it is that this kernel is measuring distances in density space between 2 densities in a totally non-local way. So by writing that down, you're representing the full sort of non-local density functional in this very simple, unbiased kind of way. And the idea is so this kind of procedure is in the class of things where you're trying to create a functional that does things that no human created functional has ever been able to do. All our standard density functionals start, in a sense, from this local density approximation, this bias towards semi-local functionals. And a lot of their failures are due to that starting point. This, from the get-go, is totally non-local. We're going for the exact functional. And within a few weeks, a very good student, John Snyder and Matthias, who were at this institute together for 3 months, were able to get very accurate energies from very moderate amount of training data. But what we found was that the functional derivative, which you also need in order to get the density when you're avoiding solving the Kohn-Sham equations, was bad. But then after a while, using a principal component analysis, we figured out how to do this projection along the directions in which you had data. And then this picture from the paper on the left here is showing that, in fact, the projected version agrees very well with the exact version for the functional derivative. And with that, you're able to actually solve the Euler equation and find accurate densities. So our proof of principle worked in this very simple toy case of one-dimensional non-interacting particles. And John made this nice slide where this is the roadmap back to reality, to something useful. And we've sort of made written papers all along this way. And at the moment, we're in this region here of looking at smallish molecules and trying to get things to work. Now, and this is one from along the way. Kevin Vu was an undergraduate with me, and this paper I like, and a lot of people use it. We did this kind of reverse engineering, not understanding how this machine learning worked. We used it to fit cosine x. And it's like all this great machinery for this very simple problem, but what you can do is then look inside the machinery and see how it does. And I think one of these curves is for our little function, and then another one is for our particle in the box. And this is looking at the landscape as a function of the hyperparameters. And you see that they look very similar. So we could use this to really understand better how machine learning works. And these were actually high school students, Brandon and Tarek, who were working with me that summer. Okay. And then, so a few years ago, I guess it came out in 2017. I'm not sure if this is my movie that I like to show. So what we did was we ran a bunch of DFT calculations on this molecule, malinaldehyde. We did MD, I think classical MD. Then we take about 2,000 snapshots of the molecule, run the Kohn-Sham DFT on that, and then make a machine-learned force field, not a machine-learned force field, a machine-learned density functional out of the snapshots. And we train it, we get high accuracy. Our projection methods that we had developed for for getting the functional derivative right didn't work. By the time you got to something that's complicated, they got too expensive and weren't accurate enough if you tried to cheapen them. So instead of just learning the energy as a functional of the density, we actually learned the potential as well. So instead of just one number, there was this vector of numbers that you learn. And what's nice about the movie is you see the proton jumping from one oxygen to another. That was not in the training set. It was after we had trained, and then we ran the simulation, we saw this happen. And of course, the energies are not as accurate at the instant of the proton transfer. And in fact, if you really want to get this accurate, you have to do quantum nuclear motion and include that. And this was mostly the thesis work of Felix Brockert, who now is part of a little startup in Berlin, one of the computer scientists. And then on the right there, we have Leslie Vogt and Mark Tuckerman, who did a lot of the work, and they're the experts in the molecular dynamics part of that. And that one was very nice and got a lot of attention. Okay. Now, taking a sort of step backwards, trying to sort of figure out what's going on with this sort of density functional. This was John Perdue was asking about, well, we use these exact conditions in DFT to improve the functionals. Can we improve machine learned functionals with exact conditions? And so what we're doing here is, let's see, we have this Hooke's atom, which is 2 electrons in a parabolic well. And we use this scaling trick, making the kinetic energy scale quadratically with the coordinates. We know it must do that exactly. And when we apply this to the, now actually, I'm sorry, but these are reversed. This legend is reversed. This is when we use the regular densities, and then when we scale the densities to impose the exact condition, we got this much better. These are learning curves. As the number of training points goes up, and you see that this is the error in Hartrees, and so this is millihartrees, and you get a couple of orders of magnitude improvement by doing our little scaling trick. So in this Hooke's atom, this 2 electrons in a parabolic well, we see that we get a big improvement by imposing the exact condition, but it turns out if you're training on H2 as a function of bond length, you get almost no improvement. And we sort of explain why that is in this paper, or we speculate on why that is. And so what it is that, yes, we can use our traditional methods of thinking about density functionals, but it's a whole different ball game when you're doing this fitting of functionals with machine learning methods, and it's less clear how beneficial they are. So a vital issue, especially with kernel ridge regression, is how you represent the data. You must kind of represent it in the right way for the machine learning to be efficient. And so this is one from Lee, who is a great, very talented coding guy who did his PhD thesis with me in physics and now works for Google Accelerated Science. And we were working on trying to do chains of hydrogen atoms, and we were doing this in one dimension because we could do DMRG calculations, so strongly correlated chains of hydrogen atoms. And could we use the machine learning methods? And he pointed out that he did a very nice trick which used PCA, principal component analysis. So I was at the Sanibel meeting one night, and I wanted to illustrate principal component analysis, which I know is used for facial recognition. So he had me take pictures on my iMac. Here are 16 pictures of my face with different expressions in order to illustrate principal component analysis. So the first thing he does is he just uses the black and white images to save computing time because he had to do this overnight, so it'd be ready for the talk the next day. So we take these 16 images of me, right? And then we average them, right? So this is my mean face, meaning my average face, right? And then you do a principal component analysis. You just look in what direction is the most variation in the data, and you look at these different directions, the most, the next most, and so forth, and express each image in the basis of these vectors. And so this is the average. And now I take one particular image and I write it as a combination of these vectors. And so if you add one principal component, you see, you can almost recognize me maybe, right? And then 2 and 3 and 4 and 5 and 6 and 7 and 8, and you can pretty much definitely recognize me, right? You can't quite get the right expression because this was the original, so it really was my mean face, right? But you see, with just 8 coefficients, you've represented all the information in those pictures, right? Or at least in a way, in a very efficient way, which can make you be able to distinguish one from another. Okay. So what he did was he looked at the chains of hydrogen atoms. He did a trick that chemists often use, Hirschfeld decomposition, to write them as densities of atoms in the molecule. He then he looks at all the different atoms inside the molecules, does a principal component analysis, discovers you need about 7 principal components, and he can represent all these different densities. Suddenly his code runs in minutes instead of days. And in fact, we were able to extrapolate to the infinite chain limit to within chemical accuracy, right? So again, as a function of the number of training examples that we have, we could get to chemical accuracy for the thermodynamic limit. And we could check against the DMRG. Okay, I got to speed up here. This is something that Bhupali Kalita, a new graduate student, is working on, where we're trying to build these derivatives in exactly from the get-go. Here's one from Isaac Tamblin, and one of his group members, and David Strube, where they're using neural networks. They're younger. They are better at the neural networks in order to find density functionals. And one of the things I like to emphasize is some people say, well, if you're working on this stuff, maybe I don't want to get into this field. And it's like, no. There's a million things to do, a million things to try. And I'm an old guy, and I'm not so good with these machine learning tools, and you really need people who understand them in order to make progress. I'd be very, very happy if somebody uses what we've done so far to see how to really make this stuff go. The next thing, I'll just very quickly go through this, is we figured out, this is Michal Bogojeski, a new graduate student of Klaus's, and the same sort of collaboration. We now use couple cluster energies to train using the same methods that we saw for the malonaldehyde. And now we use delta learning. So we look at the difference between a couple cluster calculation and a DFT calculation, and we're able to get CCSDT kind of accuracy with our method. And I'm not going to go through it all, except I want to show you, I don't have a movie yet. We've got to make a movie. But this is just an example. There's 2 different machine learned simulations, one not based on the couple cluster, one is, I think, PBE, and it's the rotation of the OH in resorcinol, and what you see is in one case it gets over the barrier, and in the other case it doesn't. So obviously when you're doing MD simulations and you're looking at some rare event, it's going to matter. Which, if your functional is not good enough, and now we can use it to do couple cluster accuracies. Its cost is still high, and it's going to scale not so great as the system size goes up, but at least you can do it. And so That's on the archive. Yeah. Okay. So in these last few minutes, how much time do I have, Stefano?
About 10 minutes or so.
Okay, yeah, that's perfect, right? So I now intend to make some rude remarks about machine learning in physical sciences, right? Stefano would be disappointed if there wasn't a section like this, right? Okay, so just generally about this whole field, right? I think we should always distinguish between experimental data versus computer-generated data, right? And experimental data is real. Computer is something we made up. Always ask, can you map your problem to image processing or not? And if you can, you should, because off-the-shelf software will get you there almost instantly, right? If you want to convince your department or whatever to get into machine learning, the first people you should always look to are astrophysicists. They love machine learning because they can do 10 times as much stuff as they used to be able to do because they can just use the software more or less. And it's been fantastic for observational astronomy. Okay. Reproducibility. This is a huge issue, right? As we'll see, I'll give you some examples, right, where, whether or not you can reproduce it. So if you grow up in physical sciences, this is a really important thing that you almost take for granted. When you write a paper, you include enough information so that somebody else could reasonably easily reproduce your calculation. That's not the way it is in computer science, because and for good reason, right? The field moves too fast. That's just a sort of slow way of thinking. They have all sorts of different standards. Basically, if an algorithm is good, other people will try it. They'll see that it's good, and it will sort of survive and thrive. But it doesn't mean that somebody else is going to put in precisely the same numbers with exactly the same random seed and get exactly the same things. Hamiltonians. All of physical science of the kind that we care about is sort of determined by Hamiltonians. When a young person, does a simulation and has a bug, they show you something, a curve, a movie or something like this, and very often you immediately look at it and you know that something is wrong. The machine cannot do that. There is all this really deep intuitive knowledge that we just take for granted, and we don't even know how to sort of say what it is, but we know when something is wrong, right? Now, obvious things wrong, yeah, and then, we check energy conservation and all these slightly more subtle things, but in fact, it's even the obvious things that the computers have no idea about. And the machine learning tools have grown up in this environment that are not determined by Hamiltonians, right? They're trying to figure out your favorite movie with your Netflix data. There's no Hamiltonian for your favorite movie, right? Statistics converge really, really slowly, right? I much rather solve a partial differential equation and study what's going on than run a simulation and look at, say, QMC statistics and wait for things to get accurate. And these are statistical methods, right? And a big problem is there are too many options, right? There are lots and lots of algorithms, lots and lots of all sorts of things, right? And anyone who's tried to work on this stuff, what will normally happen is you'll work on a problem, a few weeks, you'll get something that looks pretty good. And then about 3 years will go by when you try to make it more general and more accurate. Is this a paradigm shift? People have asked me that at conferences, and actually the term was first used by Thomas Kuhn to describe the advent of quantum mechanics, right? And so, yes, I think it is a paradigm shift. We have access, it's the computer resources that made this possible, and thinking and figuring out how to make good use of them is going to sort of change things. And it will become a whole new approach to sort of doing and analyzing science, right? But keep in mind, people don't realize this, right? Planck's constant is 1900, Schrodinger's equation 1926. You could have an entire career, scientific career in physics, studying quantum effects, and not know what the hell was going on, because it took 26 years to get from one to the other. We think now, oh, this happened, this was a revolution, it happened overnight. No, it didn't, right? So bad practices, right? And so, this is a very popular thing. And so people are in a hurry to get things done. It's the method of the day. So I would say at least 50% of the papers that get sent to me do not meet minimal standards by any stretch of the imagination. There's lots of conscious or unconscious ignoring of existing literature. People are working fast, submitting stuff, right, and they don't have time to digest what's already gone on. Lots of claims of significance because it's the first use of AI. Well, okay, that's nice, right? But, so what, right? Show me something you can do that was not possible before. There's lots of cherry picking of data sets, metrics, etc., right? And generally, I would call it sloppy science. Most of what we're seeing using machine learning in physical science, I would say, is sloppy by any standard, right? Now, of course, if it turns out to be like a really good and clever thing, maybe it's okay to be sloppy, but we have to be aware that it's sloppy, right? It isn't meeting the standards that we normally set. Some anonymous examples. Since this is going out on YouTube, I had to be a little circumspect, right? Paper A, right? From a group that is often sloppy, even before this came along, right? I rejected from one journal, it appears in another, right? Full of all sorts of things, right? And even the graphical abstract contains molecules that are not in the paper. Where's the editor, right? Paper B. So this is, it's obvious sort of when there's bad things, by a bunch of friends who are usually careful. And by the way, I should point out, none of the papers I've mentioned here are paper A or paper B, right? So don't worry, Stefano, right? I rejected it, but the editor went with the 3 positive reviews, right? It appears to be good quality, but it's not new, and all sorts of not so good things in the machine learning. And for example, there are mislabeled axes on the figures, right? The figures don't make sense. And you can see why they sort of screwed it up, right? But this is appearing in the printed version of the journal, right? This is not the kind of thing we used to allow. It was not the kind of thing that we used to get through. But this is what's happening. And a sort of, let's say, bigger picture example, this was finding, molecules for drugs, and, there was a big splash in one of the biology journals, Nature, Biotech, machine learning. They'd found a new molecule which had higher, reactivity than previous ones. And this little note from some presumably serious people in the field was pointing out that in the training set, which wasn't listed in the original publication, there was a molecule which was almost as good. But they didn't sort of mention this. This was discovered 10 years ago, the old-fashioned way, and these guys are questioning whether or not, if a person had found this new molecule, would they even have been able to publish it because the improvement was so slight relative to the old one? So there's lots of stuff that you've got to be really careful of. Okay, and the last thing I'll mention is we hear a few years ago, I was getting a lot of hype about quantum computers having big impact on quantum chemistry and material science. And the bottom line is, I would say, it won't happen within the next 30 years. It will have some impact because there are strongly correlated problems that we need solutions to. Most problems in chemistry are not strongly correlated. almost all the ones that we care about are physics problems, and it's because you have high symmetry in the solid state. So in physics applications, yes, it might be, but in chemistry, it's DFT and our standard classical methods do 99% of the work in 99% of the cases. And you wouldn't, unless you have a very, very advanced quantum computer, it's not going to be a useful thing to be running in chemistry. And the people who've been saying this with absolute confidence about 2 years ago have now backed off completely from the claims that it will revolutionize things, by next year at the latest. Okay, summary. It's a huge area with great impact in the real world. Anybody in doing theoretical science in graduate school at the moment should learn about it. I mean, in the good old days, right, we were useless. We couldn't get jobs. We couldn't eat unless we got into academia. Now you can do research and everything about be paid through the nose for it. It's good insurance. Machine learning is slowly producing new tools for electronic structure, right? They don't happen, good ones do not happen overnight, but they are beginning to appear. And making functionals, as always, is a tricky business, whether it's people or machines, right? And with that, I'd like to thank all the students, you guys for paying attention. If you did, I can't tell, all the collaborators, and this institute where Klaus and I first met, and then NSF and various divisions who helped pay for this. Thank you very much.
Thanks a lot, Kieron. Was great. So here you're going to get a virtual hands clapping in about 20 seconds when YouTube will update. But I'll start to thank you personally. As I said, about 20 seconds or so of delay. So the first question will come up essentially as you speak. So maybe I'll pop a first question. And it's a kind of a general question of something you touched at the very, very end. And it's visual errors, right? And I think, as you very clearly said, I think in physics we are at least confident with the fact that we have approximation and we more or less can navigate the approximation. We know that a band gap will not come up right if we do, LDA or something. Now, in machine learning, that's much more tricky because, strictly speaking, it's actually not this. Well, first of all, it's not that simple. And I think when people try to assess error, essentially, probably the most genuine thing you can do is to run the model many, many times and see actually what is the variance and the average of this model, and somehow this gives you a feeling of the error. I just wondered actually whether you think there is a pathway to have a more systematic approach to error when you use machine learning in general.
So there's two things. One is if you kind of really work hard with the tools, so sort of being careful and doing a lot of systematic validation type stuff, I think you can get closer to answering those questions than so if you just use it sort of out of the box the way it's been used before, no, you have these sort of randomish type errors, right? You have outliers that can be really bad and so forth. But if you do, and people have been sort of slowly learning this, right? You do these sort of leave one out procedures and cross-validation. And so in the example of the ANI1, right, what they always do is they run 5 totally independent neural networks, and they look at the parameters, the predictions that are coming out of the 5 different ones, and where their variance is large, they don't trust them, right? But that sort of procedure where you're blowing away, your cost is almost directly 5 times bigger to do everything, right? You're just blowing away that computer time in order to get that extra bit of insight is not something that people do on the first try. But it's when, so an issue, actually a very important technical issue, which I didn't mention is you notice year by year there are different concerns, different issues come up. And I would say this year's one is what we call holes, which is, let's say, take one of these force fields, or it could be one of these approximate density functionals. If you're running an MD simulation with, hundreds, thousands of atoms, and your machine learned force field is guiding the simulation, it will very often it will find some weird combination of the atoms which causes the force field to fail. If it fails in the wrong direction, of course, your molecular dynamics or your gradient descent immediately seizes on this and goes to hell in a handbasket. So this is a sort of hole in the force field. If you're running a regular Cone-Cham DFT simulation, this does not happen. And it doesn't happen because it takes care of a huge amount of implicit physics. If you start pushing some atom too far away, Coulomb will always bring you back. It'll cost too much, right? And so it'll always do something sensible. And if you're going to run this thing for, many, many cycles, it will find these holes, right? So this is something that people are really beginning to notice, and it's exactly that kind of flavor. And, then you need more data in order to fix those holes. But then there's this thing where this sort of statistical method cannot guarantee that you have a sensible calculation. If you think about DFT, right, it always gives you a sensible answer. It's often not as accurate as you would like, but it always sort of makes sense because of the built-in Cone-Cham DFT, the built-in physics. The other thing is people, especially at Google and other places, are beginning to really work on what they call symbolic regression, where instead of numerically fitting things, you try to fit functions. And I sort of spent a little time with these guys on this, and it's a very hard problem. It's a much more very sort of ill-defined space of problems and things like that. But the idea is that in certain sense, you come up with simple formulas that are sensible, and in particular, building in things like asymptotics sort of are this prior knowledge that the computer doesn't have and really constrain, what the solution might look like. And this is much more mimicking what physicists and chemists would do.
Okay, so Kieron, I have there was another question at some point, and was about the when you discussed the PCA for the representation. So I guess
Yes.
I guess the question was whether you can articulate a little bit more on that. And I have maybe a corollary question to that. Now, when you, which is about representation. So when you start to go to really three-dimensional, real density, and so on, I guess then representing the charge density start to be a really serious issue. So if you want something which is universal functional that can work with a point like a function in 3 dimension.
Yes. Yes. So okay. So this. So I maybe should have mentioned, right, these functionals that we're making this way. Actually, I don't like this word universal because I think it doesn't mean what people think it means. But let's say transferability, right? Yeah. So these functionals that we're making are I call them sort of one-off functionals. You have a given problem, and you're going to move the nuclear coordinates a lot, like you're doing molecular dynamics, and you want something that sort of works for this very, very limited range, right? So that's not what we normally do in DFT. And these kinds of functionals are of that kind at the moment, right? So they are, to some extent, we can see that the learning sort of transfers from, say, one molecule to another. that if you sort of learn with one molecule, it helps reduce errors with a second molecule, but we haven't gotten anything going yet which has the that would sort of work equally well with different, for example, different numbers of electrons. Now, some people think, oh, well, we can get around this by just making a very big box, a grid in three-dimensional space, and any system we have, we'll put it on that, and it'll have a density, and we learn about all possible numbers of particles and so forth. But if you think about that, that's just not viable. No matter how big your box is, somebody will want it bigger. And it's amazing when you think of our human-made functionals, the local density approximation just looks at the density at one point and uses that to estimate the exchange correlation energy. Well, this is infinitely transferable, right? It doesn't care where that point is, what it's in. Boom, it gives you the number. So that's a sort of difficult issue, which we have a few different things going on trying to get around that. But the ones that I showed have that issue. And it's more the idea that you want to work for a sort of specific system, get things working. And then in a separate issue is sort of, once you have that going, can you then generalize the learning on a few different molecules to give you something you can use for much bigger systems or more diverse systems.
Right.
Yeah.
And okay, so sorry, you say something else?
I said good question.
There was another question, and essentially, okay, I guess the question is, when you look at machine learning, I guess for physics, do you think that, I mean, what is the state of the art? Is typically classification work better than mapping and regression, or these are are used equivalently?
So, I mean, okay, machine learning is a pretty large field, right? There are no generic answers, right? I mean, so that's part of the point of doing that special topic was, I mean, it's like, it's as complex and diverse as our own fields, right? And if you think about it, right, I mean, what matters depends on the context, and what works depends on the context, and it's sort of very nuanced, right? So people are trying different things in different ways, and we're just beginning to really learn or to understand, let's say, what works well and what doesn't, and we don't really have general principles of, well, use regression here and classification there and so forth, or what is, and even neural nets versus say something like kernel ridge regression. These days the neural nets have become very popular, right? On the other hand, you talk to the people, often the people who know the field very well will prefer kernel ridge if you can get it to work. So there aren't generic answers to those questions. That really depend on what it is you're doing, and people are doing all sorts of things, right?
Okay, so I have another question. So let's say I ask this question, and then maybe I'll ask the next one if there is any, and then maybe we close. So the next question is essentially if you ever faced overfitting with machine learning DFT, and if so, how you deal with that?
So yes, and in fact, when I looked at some of the functionals we'd made, right, in a sense, they're all in this overfitting kind of regime when you sort of look inside. So I have to think sort of carefully about this. So again, about 2 years ago, and I spent some time in sort of math departments. what people in the sort of more mathematical end of machine learning or sort of find, there's this questions come up, which is with a lot of, trying to find parameters, right? So you run your machine learning algorithm out, it produces a bunch of parameters and it gives you predictions and they're pretty good, right? But there's these hyperparameters and so forth, and the alphas in my kernel ridge regression. You have this, a million numbers inside your neural net, let's say, right? And who knows what these mean. And you run it, on Wednesday and on Thursday, and you get a different set of these parameters, but the predictions are statistically similar, right? So what people have found is that often there are multiple solutions, and you tend to be in these basins of the hyperparameters that are very shallow and broad. And so it means that whatever the values are, you get roughly the same answer. But it's this overfitting where there are many combinations that will get you this kind of answer, and the combinations look different from each other, but their predictions are all the same, or just about the same. So, which is, doesn't make me very comfortable from my normal way of thinking about things, right? And again, this is related to, these general questions of, can you understand what the machine did, right? And, if it randomly is selecting these things and you plot them out and they look totally different, how the hell do you understand that, right? Obviously, looking at these parameters and things is not the right way to think about it. Okay. In some sense, you look at predictions. Yeah.
Okay, so as you said, this is the last question. And the last question essentially is the following. So it's about what is your opinion about using, say, neural network as a variational Monte Carlo method for creating ansatz for the wave function?
I think these are all, this kind of thing is very good. I think over time I've seen the sort of relations between machine learning entanglement and sort of tensor product decompositions, tensor product states. I think we are slowly beginning to sort of make connections between these things where, machine learning, all these different algorithms are very broad and can be applied to lots of things, but then in sort of with certain restrictions, right, that they sort of begin to, in some sense, almost overlap, right? And they're all kind of ways of extracting sort of from very complex situations, a sort of minimal type representation of what's going on, and a way of, and I think I sort of tend to think of it as some people are using it to find, say, collective variables in molecular dynamics simulations, and it's sort of where hidden inside a complex system is a description that's simpler, but it isn't the one that you get from your textbook. If all our textbooks are written in a way that sort of simplify pictures where you don't have a computer. You write things in terms of eigenstates. We love to do our derivations and things like that. But when the underlying simplicity is not something that's in terms of the elements we use to think about where it came from, then I think a lot of these methods are what they're getting at is underlying it. So, and another way to put this is the Schrodinger equation, right? That Schrodinger equation that I wrote down, is very painful to solve. On the other hand, the Hamiltonian is ridiculously simple. It's the same damn Hamiltonian over and over again. So there's no reason why there can't be lots of simple patterns And we know there are simple patterns in the solutions to the Hamiltonian. And if you can find those patterns without having to do what, centuries of mathematicians have told us to do, of solving the differential equation, then it sort of makes sense. But that pattern is not the one that we're used to looking for, right? It isn't the one where we analyze the differential equation and try to solve it approximately. Yeah.
Okay, thanks a lot. And okay, so I guess maybe we should close here. So let me thanks Kieron again, and all of you who have listened to this. And we are going to have a new seminar next week at the same time. Thanks, everybody. Thanks a lot.
Okay. Thank you, guys. And thank you, both of you, for tuning in and listening.